And I'm happy to introduce today Christopher Kapler, who's the CEO at Achilles Test Systems. Prior to Achilles Test Systems, Christopher worked at Cisco Systems as the lead architect of the Quas engine in the Cisco Quantum Flow processor. Prior to that, Christopher led an architectural group at Hammerhead Networks, which was acquired by Cisco in 2002. Since 1992, he's worked on ASIC, EDA, and embedded software project at companies many of us know, such as Seaport, Meta Systems, Mitsubishi, UB Networks, and Sun Labs. Christopher has a PhD from Syracuse University in computer systems engineering. Please welcome Christopher.
So, as Paul said, I've been in the Boston area for about 14 years now, and I've done a few different types of work. These are the positions we mentioned. The great thing about the Boston area is that a single engineer can do RTL, can do embedded software, can do EDA work, and you don't even have to get off Route 95 to get it done. So it's a fascinating area to work in, and the work that I had done at Cisco was some of the most formative because it was a real introduction to trying to leverage corporate resources to the best of one's ability to attack a really difficult problem and to gain confidence that it was being done to the degree that it was necessary. The lessons, though, that were learned on that project are applicable to pretty much any SoC. And so I'm just curious, from the work that we've done talking to people over the past 2 years as in Achilles, we found that there are fewer SoCs going on these days. I think there may be only 2,000 SoC starts per year. So are there people doing SoCs in the audience? So actually, maybe a quarter of the audience. And FPGAs? All right. And then everybody else is in software or EDA. But what characterizes a typical SoC is the innovation that's required to get it off the ground. The cost is such that the innovation has to justify the time frame of getting the work done and the bodies applied to the job and the tools applied to the job. And so you're often trying to leapfrog not just the current generation, but often leapfrog the next generation in what the features are going to be. And to get that done, these companies these days are multi-site, very distributed. You're getting some IP from remote vendors. You're getting expertise from different sites around the country, around the world, and very specialized teams with different disciplines, such as physical design teams or verification teams, specific feature teams, take video processing of various types that we see done. And so the challenges are how to maximally leverage these resources, to leverage not only your corporate resources, such as your licenses and your server farms, but to leverage your expertise and to get people really moving in the same direction and maintaining their focus and momentum as the project goes on. And so how to achieve that leverage is basically through information, communication, collaboration. The obvious things that any organization chart tries to achieve, that any company wants to foster. We just want to apply technology to help get those goals met. And so, for example, to use hundreds of CPUs or thousands of CPUs, it can very quickly become overwhelming for an engineer. And so to invest in the environment, you're going to want to create enough underlying technology to help leverage those resources without becoming too much for any one engineer to handle. But when it's done, you can get 2 orders of magnitude improvement. So if a single engineer today can achieve maybe 10 tests a week of coding new tests, with the right technology, maybe you're looking at 100 or 1,000 tests a week coming out of each engineer. Likewise for the number of executions. You might run 5, 10 executions a night, and if you're checking by hand, process those. But if you're applying the right tools to the problem, you might be able to run 100 or 1,000 tests a night per engineer. So the techniques that we're going to talk about today are not new. If, for example, here, other DV Club presentations that have gone on in the past couple of years essentially overlap the techniques that we'll talk about today. And so, has anybody attended any of these, specifically the 2004 talk in the Boston area? Anybody attend that one? All right. So most of these have their slides posted on the DV Club website. It's great information up there, as Paul was just saying. It's a fantastic resource. And but what we're seeing, and actually let me ask you again, is anybody in the testing phases, is anybody following a classic water flow model where first the architectural testing is completely finished, and then the RTL testing goes on, and then it's completely finished, and then the lab testing goes on? So nobody. All right, and what about on the bottom, where in a multi-million dollar, $100 million SoC, where the innovation is such that there are still requirements questions being asked all throughout the RTL testing phase? I'm seeing some heads nodding on that one. And in the FPGA, where either the architectural testing is doing the same thing as in the SoC, or else requirements and RTL requirements and performance questions are being answered in the lab, and lab testing is going on in parallel with RTL testing. And so the focus is on multiple model types being used at the same time, and to be able to leverage and cross-pollinate the work that's being done at each of these layers of abstraction, and not let time or effort be wasted, and only do things once. They only have to be done once, and reuse that technology when possible. So to plan for the first pass success of a large project, assuming, say, a typical SoC flow, you need to budget for the resources that you're going to apply to the problem. And so start asking, okay, well, how many CPUs, for example? Projects could have 5, 50, 500 CPUs. I think PsyCortex has got a few more applied to a given problem. And then you figure out what an average test is going to cost. So in the quality of service domain, a test might run for 2 hours on the CPU. And so assuming 1 to 2 hours per test, every CPU is going to do about 12 tests. And so if you have 10 CPUs, you might get 120 tests a day or 44K tests a year. If you get 200 CPUs, you might get almost 1 million tests a year. Now, 1 million tests a year sounds good, but you need to not let that become an overwhelming factor on the project. You need to not bog down your verification team handling that. In addition, you have to run productive tests. Nobody wants to burn the power to run 1 million tests on hundreds of CPUs 24 hours a day if the results aren't going to be used, or if the tests are redundant or wasteful or aren't creating new coverage. And so the obstacles to overcome, especially with a small team, are how to create tests, especially for a next-generation product that might have feature sets that haven't been supported up until now. And how to create the tests, and how to, in an architectural case, when we're overlapping architectural testing with RTL testing, how to get often the millions of cycles per test that you might need to achieve confidence in the results that the design really is meeting requirements. And so one sort of anecdotal good idea that could be applied is to create a test description language that resembles an end-user production language, an end-user deployment language for your product. And so in the networking field, for example, a simplified command line interface could be employed as a test description language. The advantage to using an end-user-centric test description language is that you can start to leverage some of your corporate resources that might not have normally contributed to your testing effort. You can get your architects and your marketing folks, you can get your QA team and your software team involved in helping you define what are the important configurations that we've seen. What have our customers asked for? What have been problem scenarios before? What's come in as a serious bug report that we've all had to deal with? And so defining your tests in that language allows you to take advantage of corporate resources that might not typically contribute to RTL testing. Additionally, by constructing your test environment with a little bit of modularity, you can leverage expertise of your software team that might not have typically been available to you. So architectural testing usually goes on early in the design, long before a register definition would have been made. And so what you need to do is create a configuration API, which is higher level than what your register API will be, and allow for your architectural testing to configure via that config API, but assume that your product is going to be configured the same way. And that way, you can put your operational software on top of your architectural model, or vice versa. You can put your architectural testing code on top of either your reference model or your actual RTL when it comes up. So a little bit of software modularity goes a long way, and the software team is just a gold mine of expertise on important configurations and what realistic configurations are. And also sometimes you want to know what not to test, what holes not to go down, because there's a lot of work to do. So then